So, what we're moving on to now is the discussion of capacitance, and here is a flux capacitor from the movie Back to the Future, but unfortunately we're not talking about those. What we're actually talking about is electrical capacitance. And by electrical capacitors, this is something we've already seen before. In terms of capacitors, what we're talking about is a system of two conductors that have equal but opposite charges. And we've usually seen this in the context of a parallel plate capacitor. In the parallel plate capacitor, our situation is we have two plates, one with a negative Q on one plate and another with a positive Q on the other, positive and negative charges on each plate. And this is the typical diagram we've seen before, and we looked at the electric field within these plates and calculated it using the formula E equals V, the voltage across these plates, over D. So when we set up a voltage by hooking this capacitor up to a battery, we'll end up with an electric field running across these plates. So what actually is a capacitor? In the case that we're looking at here, a capacitor is a device that's capable of storing short-term energy. That means we can put charge onto a capacitor, and then by hooking it up to another device such as a resistor, like a bulb or some other similar device, we can discharge that capacitor in one burst. So unlike a battery, there's no induced EMF, so the charge is not replenished by the device itself, but has to be put onto the capacitor from a battery. The plates, in the case of a capacitor, that's in a computer or other electronic device that you might have in your home, are not actually just two large metal plates. They're usually in the form of either a cylinder or a small flat circular device that if you open up any device in your home and take a look, you should see. These are because it really becomes much more convenient in an engineering fashion than have these large square objects. So here you can see a range of different capacitors. Here are the kind of capacitors you might have in a computer or TV. These capacitors here are much bigger, charge much more, hold much more charge, and are probably used for some industrial processes. Inside one of these larger capacitors, this is what you would have. Here's our connections to our films inside, and then we would actually have two pieces of conducting film wound up with an insulator in between them, some kind of plastic film to prevent contact, which also acts as something called a dielectric, which is something we'll talk about in the next set of slides. When we're looking at our circuit diagrams, and we've already looked at circuit diagrams a little bit in one of the previous lectures, what we'll see is a capacitor drawn either like this, we have a plate and we have a circle. This is the older version. Probably won't see that in my lectures or in the book. You'll see this more current, conventional version of two parallel lines. So like a battery, we have a positive and a negative plate. But unlike the battery, there's no EMF induced. There's no voltage that's maintained by the device itself. In the context that we looked at capacitors before, we looked at the capacitor and talked about the electric field set up between the plates. And we always said that electric field was uniform. And that is true anywhere between the plates. As you can see, these lines are very uniform. Just outside the plates, they tend to curve around. It can no longer be trusted to be uniform in nature. But inside the plates, E is a relatively uniform environment. This means that electric field set up between the plates is transferring charge from one side to the other. The negative plate is this plate is gaining negative charge. It is being pushed across by the battery. So the battery is doing work to move electrons from one plate to the other, leaving us a net negative charge on one plate and a net positive charge on the other. Here, remember, our guiding equation was E is equal to the voltage V divided by D, the separation. So in terms of our capacitor, here's a typical circuit diagram. Here's a battery, a long line and a short line parallel to one another, and here's a capacitor represented by two long parallel lines. The potential difference or voltage across the battery is equal to the same across the capacitor. So a charged capacitor is effectively storing energy. Excuse me. So our capacitance, the ability of the device to store charge, is given by this simple equation that C is equal to Q over V, the potential difference across the plates. So capacitance is actually in the unit of farads, and the farad is one of those large units, so you'll often see 10 to the negative 6, 10 to the negative 9 farads in the examples we will look at. Q, of course, is in coulombs, which confusingly is another C that you will see in your calculations. So don't confuse coulombs of charge with C for capacitance. And finally, voltage, or potential difference, which is given in volts. So with this in mind, if we have a 5 microfarad capacitor and hook it up to a 10-volt battery, what would be the charge on each of the plates? In a question like this, we can simply invoke C equals Q over V. We want charge, so we're rearranging this 3-variable formula for Q. So Q is equal to C times V. C, remember, has to be put into farads, so we have to convert our 5 microfarads into farads. So this will be 5 times 10 to the minus 6 farads times 10 volts, giving us 5 times 10 to the minus 5 coulombs. This is usually rewritten in terms of microcoulombs, so this would be 50 times 10 to the minus 6 coulombs, or 50 microcoulombs. So we can also define another definition for our capacitors. So if we look at the capacitor from the perspective of the electric field and then invoke C equals Q over V, we can say that Q is going to be some charge per unit area. If you cast your mind back to Gauss's law, we looked at sigma and talked about the distribution of charge per unit area along cylinders and along squares. So C equals Q over V, which is equal to sigma A over E times D. We can redefine E in terms of sigma, the charge per unit area, over the permittivity of free space, epsilon 0. If we use this for E and we use this definition for Q, then we can say Q sigma A over sigma over epsilon 0 D. Well, we can cancel sigma. This will come to the top here, and we'll end up with a new definition for capacitance, where C is epsilon 0 A over D. Remember, the epsilon 0, or permittivity of free space, is 8.85 times 10 to the minus 12 farads per meter, or 8.85 picofarads per meter. So let's take a look at a quick problem. If we have a parallel plate capacitor with sides of 10 centimeters separated by 1 millimeter, we can calculate the capacitance of this particular device. Remember, these units are a bit mixed here. This is in centimeters, this is in millimeters, so convert those immediately. So invoking C equals epsilon 0 A over D, we can simply substitute in 8.85 picofarads per meter times 0.1 meter squared divided by our separation of 0.001 meters gives us 88.5 picofarads. Very small capacitance, as I pointed out before. If this capacitor is charged at 12 volts, how much charge is then transferred from one plate to another? Now we can use our other definition of capacitance and say Q is equal to C times V. C will be 8.85 picofarads from our previous part. 12 volts is the voltage that a capacitor is charged to. So Q equals CV will give us 1.06 times 10 to the minus 9 coulombs. This is a nanocoulomb, or 1.06 nanocoulombs. So if we look at our system that we just calculated, The Q, the charge in that case, is 6.6 times 10 to the 9 electrons. That's how many electrons will make up this charge of 1.06 nanocoulombs. Remember, the charge on the electron is 1.6 times 10 to the negative 19 coulombs. So for a capacitance of 1 farad, remember 1 farad is a very, very big unit. We would have to have a plate that was 1 times 10 to the 8 square meters in area. The reason being that when you have like charges put onto a plate, they will repel from one another and want to get as far away from one another as they possibly can. Consequently, if we had a 1 farad capacitor, that capacitor, if it was made as a square parallel plate, would wind up being 10.6 kilometers on a single side. So, most capacitors that we see in our cases are going to be in the micro to picofarad level. So micro 10 to the negative 6, pico 10 to the minus 12, or we might see nano farads 10 to the minus 9 farads in some cases. Remember, if you make a mistake and drop your negative and have a 10 to the 6 farad capacitor, that's probably the size of a hemisphere on the Earth in terms of a capacitor. So in terms of charge storage, if we have a small amount of charge delta Q and we move it between our plates from the negative to the positive conductor, the potential energy of that particle will change by delta U, or PE as it's written in some cases. That potential energy is going to be V, the electrical potential, times the charge delta Q. Remember, we have a difference here between electrical potential and potential energy. Make sure you don't mix these up. So if Q is the charge that's transferred during charging, the potential difference V will be Q over C. This means that our potential energy that's stored in our capacitor will be equal to the electrical potential times Q. Delta U will be V times Q, or Q over C times delta Q. Consequently, this gives us several definitions that we need to remember. This first one tends to be an intermediate step that we don't need nearly as much, but the potential energy now stored by a capacitor that's governed by C equals Q over V will be 1/2 Q squared over C. That will give us 1/2 Q times V. Or, if we put this in terms of capacitance itself, 1/2 CV squared. So where did that come from? Well, in terms of charge storage, this goes back to something very similar to when we looked at Hooke's law, when we looked at F equals kx for a spring. We found that the work done by that spring was 1/2 kx squared. We see a very similar relationship here in that V versus Q, voltage versus charge, being plotted as this nice straight line here, will end up giving you this nice triangle. If we actually do calculus on this and figure out the work done, it turns out to be the energy beneath this triangle and ends up being 1/2 CV squared. Consequently, we can use these equations. So how much energy here, not potential, but how much energy can be stored in a 15 microfarad capacitor at a potential difference of 60 volts? Well, the potential energy here is 1/2 CV squared. We have all the values we need, substitute in, we'll end up with 1/2 15 times 10 to the minus 6 farads, microfarads, times 60 volts squared. This will give us 7.5 times 10 to the minus 6 times 3600. This will give us 0.027 joules. So a 15 microfarad capacitor with a potential difference of 60 volts will store 0.027 joules of energy. Remember also, for our parallel plate capacitor, we could relate the voltage of the system to the electric field and the separation of the plates by V is equal to E times D, where D is our plate separation. Consequently, if we look at this in terms of the electric field, we can say a uniform electric field is established by connecting the plates of our capacitor. If we have a 12-volt battery hooked up across our terminals and the plates are separated by 0.63 centimeters, watch the units, what's the magnitude of the electric field in our capacitor? Also, what's the work done if we take one plate and move it by 1.5 millimeters? So mixed units again, double question. Let's try and solve this one. Remember, the force on oppositely charged plates is going to be attractive between them. This is a negatively charged plate. This is a positively charged plate. They will want to get together and discharge between one another. So the force on the upper plate is positive QE due to the negative Q on the lower plate. That means the electric field is half of the total field between the plates, as the charge on the upper and lower plates are both contributing equally to the electric field. So let's calculate E. So when the potential difference is 12 volts and the separation is 2 millimeters, the total field strength between the plates will be E equals V over D, or 12 volts over 2 millimeters, which will give us 6 volts per millimeter. The magnitude of the force now will be F equals QE. Go back to our previous definitions when we looked at the force on a charge. This means E here will be Q times 1/2 E. That will give us 1.04 nanocoulombs times 3,000 volts per meter, kilovolts per meter. And that will give us 3.12 micronewtons, or 3.12 times 10 to the minus 6 newtons. But this was not the whole question. The rest of it said, what is the work done to move the upper plate by 1.5 millimeters? Now we actually have the values we need here, because we can go back to mechanics and say work done is force times distance. W equals Fs, or F delta D. We have our value here for F that we just calculated in the previous case, so we can say 3.12 micronewtons multiplied by 1.5 millimeters. Remember, this is 10 to the negative 6, this is 10 to the minus 3, will give us 4.68 nanojoules, or 10 to the negative 9. So negative 6 plus negative 3 will give us 4.68 times 10 to the negative 9 joules. So as we said, in terms of charge storage, capacitors are usually charged by a battery. They can be charged by a generator in some cases, but here we're going to deal with a battery. And this maintains a potential difference, a voltage between its terminals. The work done by the battery in delivering the charge to the capacitor is equal to Q times V. That's double the energy stored in the capacitor. Additional work is done by the battery, much more than that, as some energy is lost in the form of heat and resistance in the wires and EM radiation from the battery itself. So batteries are quite inefficient things, and we cannot account for this. This is a bit like trying to account for friction in case of moving a block up a hill. So capacitors, as we said, are usually charged by this battery, and the work done by a battery in delivering charge is Q times V. How much charge times the potential difference. And that's double the energy stored in the capacitor. So next time we're actually going to talk about capacitors in circuits, how to add them, how they behave, and how we can utilize them to build actual circuits. And here we've got a battery hooked up to a capacitor, hooked up to a bulb.